We're in New Mexico.
So we're in New Mexico, University of New Mexico.
Yeah.
About to visit physics laboratory.
Let's have our minds blown.
I'm okay as long as we're not
First
going
part,
to
small
Brothers
apples. They developed
The technology.
Developed the technology
Very
for
small
tiny apples.
Yeah.
So,
that's the first thing.
and they changed the color too, but we're not going to get into that.
See,
No,
that's
we
when it
won't.
starts going
That's
red.
their death ray right there.
This.
They just have that label on there to, you know, for the public. They can't know about it.
There he is. Going underground. Your umbrella to Raccoon City. Umbrella Corporation.
Raccoon City?
That's
Yeah. Take you guys to the basement.
Umbrella Corporation? Can it be a test subject?
Depends on what you want to test.
The TC virus. Whatever it's called. That's awesome.
Okay, so this is like, these are the halls where they do, a lot of the department experiments are here. And we'll go all the way down to the end. We're down in the basement. This building's kind of like a labyrinth. Like sometimes when the theorists that work in the other part of the building come down, they've never been down in the basement. They, been work here for 30 years, never been down there. Then we show them our lab and everything, and then they get completely lost and confused, and we have to escort them back to their office. Yeah, theorists.
One down.
The whole thing flows and completely damaged.
That's like a restricted.
And then we're right below the machine shop, which restricts every extra careful because anytime you have one of these giant machines going, the whole, their room vibrates a little bit, a tiny amount of vibration into the building, which we can completely see.
So they don't rollers.
Not exactly on rollers, but I'll show you what we got.
Laser radiation classifier.
Oh, it's linear
Well, of course.
on the L.
I just found this one on the internet. Because if we have one of these lasers on and you take it to the eye, you'll definitely pop your eye. But it's all off right now.
Yeah, but can you make my vision better?
So I guess I can show you on this one because this one's very misaligned. So this isn't the experiment that I'm exactly working on. These are like two kind of like side experiments to the two main ones. But this is what a lot of this shit looks like. And like to protect from vibrations, you see like if you look down, look at these legs right here. So they're like, it's like a leg right here, but it's like a pneumatic valve. So it's all floating on air. So if you were to push this down, the whole thing bounces. And so like if there's any vibration in the building, the table, every single one, it's a bunch of optics and stuff in all of these boxes.
Yeah.
This is a
Big ass laser system in here. Big ass laser system in here.
This is the laser that if you take it to your eye, you're definitely fucking blind. Yeah, totally. And but so like all of these here, we put boxes around it for both stability and for safety. So that way, if something gets messed up and the laser isn't bouncing off a mirror, then instead of going somewhere in the lab where you don't know where it is, it gets blocked by this box. And so you might burn this paper, but you won't burn out your eye.
Yeah.
I'll take that any day.
Yeah, exactly.
So these lasers, what are they used for?
So I've got, let's see, 1, 2, 3, 4, 5 lasers on this table for my experiments, of which 4 of them I'm using right now. And 2 of the lasers are used to cool and trap the atoms. So I was saying yesterday that we have we cool and trap atoms with the combinations of lasers and magnetic field. We're able to trap them and cool them to really, really low temperatures. This happens over here.
Can bounce the lasers off the crystals?
You can, and that's actually analogous to what we do, like in the long term of our experiment, but we actually don't do any stuff with crystals. But there's things called nonlinear crystals, which we basically use ultra cold atoms instead of nonlinear crystals. So we know like a lot of people that do nonlinear do use crystals.
Oh, I see. No lightsabers.
No lightsabers.
That's not my
quite
kind of
yet.
crystal. I'm all about the linear.
You just need to figure out how to trap the beam.
So where do the atoms hang out when you're bombarding them?
Yeah, so all the atoms are right here. So we have a vacuum chamber here that's made out of mostly stainless steel, and then there's the glass part where we actually do like part of the experiment, and we like basically heat it up and suck all of the air out of it. This is our like a pumping thing. So there's 2 different pumps right here, and then with that we're able to suck all the air and all like the crap that's in there out of there and make it like an ultra clean, ultra pure environment.
Yeah.
The pressure of here is so it's 10 to the negative 10 torr, so it's 13 orders of magnitude less pressure than the atmosphere.
Okay.
So it's fucking, there's basically nothing in there.
Yeah.
And then, so what that allows us to do is then we have just a very clean, very pure environment, and we get just one particular kind of atom, cesium, and one particular isotope, and we're able to have just this one isotope in there, so we have a very clean environment to have all of the cesium, our cesium interact with the lasers. And so we have like a kind of very dilute background gas of cesium in our vacuum chamber, and then with one of our lasers, we lock it to the other laser, yada yada yada. And then we have the lasers coming out here and spread into 3 different beams. So we have 3 different laser beams that are all about this big around, one's coming in this way, one's coming in this way, and one's coming in this vertical direction, so that they're all kind of meeting right in the center of the cell. And then we have mirrors on the other side, so we reflect the laser back on itself. So you have like a laser this way, a laser this way, and a laser coming down and then reflected back. So you have like 3 pairs of counter-propagating beams all intersecting in one region. And in that region, we also create a very well-defined magnetic field with these coils. So these are just like, basically, I hand wound these. So I had I designed these parts to be exactly the size and got them 3D printed, and then hand wound it. This is just like good wire.
Yeah.
And then by putting like current through it, you're able to create a magnetic field. And so we create a magnetic field with these coils and then have all these lasers with very specific frequency polarization. We have like very well controlled beams and the properties of the laser light, and it all interacts right in the center. So when the atoms interact with the lasers and with the magnetic field, they cool down.
Gotcha.
And so they cool down right at the center where all of these 3 pairs of beams all intersect. And one kind of way that you could think about it is the atoms are kind of like bowling balls, just going in like, just from the temperature that they have, just from being at room temperature, they're just going in every direction. But the way that the lasers work is that whenever one of the atoms is going towards one of the laser beams, because we have like 6 coming like that with the reflected one too, it's basically like the laser beam kind of acts like one of the guys in the department describes it as like a machine gun of ping pong balls. So you have like a bowling ball, and then you have a machine gun of ping pong balls, and so like, so what happens is that the atoms like scatter a bunch of light, so they absorb and re-emit these light, and you just do this over and over and over and over again, so you slowly slow down the atom.
Yeah.
And as the atom goes slower and slower, that's what makes it cold.
Gotcha.
So it's because it's not interacting with anything. So that's how you kind of define the temperature here, is that you make it so it's basically, it's not exactly freezing it because it's not in like a crystal structure.
Yeah.
It's just like amorphous, but so it's still a dilute vapor, but it's really, really slow, and like you get them moving really, really slow.
Okay.
All the atoms in all directions. And so that's how we make our ultra cold ensemble. And so I have a picture of one of them. Oh, it's probably this. Yeah.
I think
Is that what was it?
It was something
Ultra
like
cold
that.
ensemble, yeah.
That was what I wanted for my future jazz band.
Cool ensemble.
Hell yeah. That's awesome. So it looks something like this. So it looks like just really bright blob right in the center. And you can't exactly see it with your eyes just because the color of the light is outside what our eyes can see. But it's pretty close. So our eyes can see about to 700 nanometers of light, and this is at 852. So it's kind of just like outside the range we can see with our eyes.
Okay.
And so what this is here, it's like the edges of this photo here are So this photo is of this TV screen,
Uh-huh.
and what we're looking at, this is the image from this camera. So this camera is looking at this mirror, is looking at that. So these edges that you guys can see right here, that's like the edges of this glass right here.
Okay.
And so this is actually a relatively large ensemble compared to what other people in other labs do. A lot of people that do research with ultra cold atoms have like basically like 1 millimeter by 1 millimeter little blobs, but this one's like a full fucking inch long. So
Yeah.
this is it's like a long ensemble, so you can get, so I can then later get a really strong interaction of this atomic ensemble with additional lasers, which is where my research actually is.
Cool.
The new stuff that we're doing. So people that developed these techniques got the Nobel Prize back in the 1996 or something like that.
Really?
Yeah, but now they've become like the workhorse of cold atom experiments, so it's like relatively common. But
Yeah.
this one, when I have it going, that little region of space, those atoms, that's the coldest thing in the state of New Mexico. This
Really?
is fucking sweet. Yeah. Atoms, and then we have 2 additional laser beams coming in like that, and then these 2 additional laser beams interact in a couple different ways, but interact with the internal energy structure of these atoms to drive what we call like a non-linear process. And it's so what it is, it's a spontaneous 4-wave mixing process, and what that means is basically the atomic ensemble absorbs 1 particle of light from each of these additional laser beams, and then emits 2 particles of light. These 2 particles of light that are emitted, that's what our research is about. And so we're looking at the quantum correlation of this.
Sorry.
No,
Trying to be
please.
discreet.
Yeah, I'm trying to not look good.
You gotta get good at this, dude.
Yeah.
Future documentary.
Yeah. You're gonna
Yeah.
have cameras in your face for the rest of your life.
Fucking A.
So you're studying these 2 photons that are emitted.
Yeah, exactly. So this is a photon pair, an entangled photon pair. So we look at the quantum correlation of basically the spatial structure of this photon pair. And what we want to do, and that's basically the novel part of our research. So pretty much everything I described up till now has been developed by other people, but what we're developing is a thorough study of the spatial structure of these photons. So basically what it is, so if you think of like a laser pointer, it's just like a dot, right?
Yeah.
It's just like a round dot mode. So these photons that are emitted in this process, they don't need to just be in a round dot. There could be like deformations, or there can be different structure to what they actually look like. Instead of having 1 dot, it could be 2 lobes, or it could be 4 lobes, or it can have different structure.
Yeah.
And so what we study is exactly that structure, and basically how we can use kind of that structure to communicate large amounts of information securely. And that's what the application was I was talking about earlier about quantum communication. So these are kind of degrees of freedom that have quantum information in them, and so you can have high capacity quantum communication